Today we will talk about buck converter. Control the DC source using a pulse output voltage is insufficient. We want to produce an output that is more purely. The diode here is used to provide a path for the inductor current. One way of obtaining a DC output is to insert a low-pass filter. This is how buck converter comes. Before we start analysis buck converter, I'd like to introduce some common DC-DC converter properties. So first of all, inductor current is periodic, which means the current will go back to the same value in every period. Second, the average inductor voltage is 0. And third, the average capacitor current is 0. And the last one is input power is always same as output power. We use these properties to examine inductor and capacitor in the converter. Let's first analyze when the switch is on. When the switch is on, the circuit looks like this. Let's first analyze inductor. I'll draw the current and voltage waveform at the left-hand side and while we are doing analysis. The voltage across inductor is Vin minus Vout. So we'll put Vin minus Vout here. Also, we know the inductor voltage is equal to L times di dt. After rearranging, we can know that the current ripple divided on dt equals to Vin minus Vout divided on L. By this way, we know the relationship between the current ripple and inductance. Since the derivative of the current is a positive constant, the current increases linearly as this. When the switch is off, the equivalent circuit looks like this. The voltage across the inductor is minus Vout. And we do the same thing as when the switch is on. We also can use this equation to calculate current ripple. They are same. Steady-state operator requires that the inductor current at the end of switch cycle be the same as that at the beginning. So around the average current, the inductor current goes like this. There are a few other things we can get from inductor analysis. First, the net change in inductor current over one period is 0. So we know that the delta IL in on stage is plus delta IL in off stage should be 0. Using the equation we derived before, we can solve the V out as V in times D. This is also the second important equation we derived from the circuit. Second, since we know the change in inductor current, the maximum and minimum value of inductor current can be calculated. The maximum inductor current is the average current on inductor plus delta IL divided on 2. And I forgot to mention the average inductor current is actually the output current, so which is the V out divided on R. The minimum inductor current is IL minus delta IL divided on 2. From here, we can analyze the continuous current in the inductor, aka CCM or DCM. Why DCM? When load increase, the average current decrease. To some point, the current is so low, so in a little period of time, there is no current on inductor. I minimum equals to 0 is the boundary between CCM and DCM. Then let's move on to analysis capacitor. The current on the capacitor is inductor current minus output current. So we can easily get the capacitor current like this. In the preceding analysis, the capacitor was assumed to be very large to keep the output voltage constant. In practice, the output voltage cannot be kept perfectly. The voltage ripple is computed from the voltage-current relationship of the capacitor. So now let's calculate the voltage ripple. While the capacitor current is positive, the capacitor is charging. From the definition of the capacitance, we know that Q equals to C times V out. And from the current waveform, we know that the change in charge is the area of the triangle above the time axis. So by equal these two equations, we can find the relationship between voltage ripple and the capacitance. Finally, I want to talk a little bit about RMS inductor current. I find some of you forget to divide the 2 on current ripple when you do assignment 1. So yes, you need divided 2. Don't forget it in your final exam. For the questions in the tutorial, I will not repeat the answers again in this video. The solution is already on Canvas. You can follow it step by step. I'll only give you a little bit summary here. There are 2 types of converter questions. One I named it as exam questions, like your 6.5 and 6.7. Another one I named them as design questions, like your 6.6. So for examining questions is they give you all the parameter in the converter and you need to calculate the current and voltage ripple to see if it's a good converter. So usually you know V in, V out, duty, inductance, capacitance, and frequency, and you just check the current ripple and voltage ripple. For design question is another way. You know the current ripple, voltage ripple, and V in, V out, and you need to design the duty cycle and design the capacitance and inductance. So basically you use the same equation but in different way. First equation you might need is the duty between V out and V in. Just try to rearrange the equation, you will find the value you need. The second one is the ripple and inductance relationship equation. Yes, as you see, it's the same equation and you use it differently. And the third one is our voltage ripple equation. Again, just play with the equation and you will find the value you need.